Hello everybody, it is 4 o'clock and I would like to welcome all the participants to this webinar on high resolution and gapless dual-com spectroscopy with current-tuned quantum cascade lasers. I'm very honored to have Lukas Emennecker and Michele Gianella be co-host of this webinar. First, let me give you some information. You can send questions. Please write them or post them in the Q&A chat. We will collect them, or I will collect them, and at the end of the webinar, we'll have an extensive Q&A session where we will address all of them. But please feel free to already write some questions during the webinar. Whenever it pops in your mind, just post it. We'll collect them and we'll answer it at the end. So let me give a quick introduction to Lukas Emennecker and Michele Gianella. Lukas Emennecker is the head of the Laboratory for Air Pollution and Environmental Technology at EMPA in the ETH domain. He received his PhD from ETH Zurich and has 30 years of experience in research, engineering, and teaching within private and governmental institutions. His main interest is combining measurements and modeling of anthropogenic air pollutant relevant to climate change and human health. This includes groundbreaking work in the mid-infrared laser spectroscopy for high precision, real-time analysis of trace gases and their isotopic composition. Lukas Emennecker has contributed to over 140 research papers and is co-founder of 2 spin-off companies in the field of laser spectroscopy. Welcome, Lukas. Michele got his master's degree in physics from ETH Zurich in 2006. He did his PhD in the spectroscopy group of Marcus Sigrist on analysis of circle smoke by infrared laser spectroscopy from 2007 to 2011. For his outstanding doctoral thesis work, he was awarded the ETH medal in 2011. He then worked as a postdoc in the group of Marcus Sigrist in the IRSense project, where I had the honor to collaborate with him. The project was on optical sensing of cocaine in liquid solutions. From 2013 to 2018, Michele was a postdoc researcher at the University of Oxford. He was awarded a Marie Curie Fellowship. The objective of the project was to develop a sensor based on laser spectroscopy for the medical diagnostics of one or more human diseases by measuring biomarkers in breath. He also worked on intracavity Faraday modulation spectroscopy for the detection of radical species, in particular peroxy radicals. In 2018, he joined the research group of Lukas Emennecker as a senior researcher and is the driving force behind the success story we can present today in this webinar. So with this, I would like to switch to the agenda. I will give a very short introduction to this dual-com spectrometer, the Iris F1 that IRISweep is selling. But then I'll give the stage to Lukas and Michele. Lukas will give you an introduction on the dual-com principles using QCLs, and Michele will then show his results on high-resolution gapless dual-com spectroscopy. At the end, we're open for questions and answers. So the Iris F1 is a complete dual-com spectrometer. You see it on the top left. We're basically selling a spectrometer which is inspired by FTIR. It's a tabletop instrument. You get an optical bench, you get a computer to drive your instrument, and in the rack you have electronics and processing hardware. It features very easily exchangeable laser modules. You see on the bottom right. Basically, this module that our collaborator carries there is a fully dual-com unit. And if you want to change from one spectral region to the other, it is as easy as changing this module, and the instrument will recognize the new module and will then basically turn the lasers on in a good COM regime. The benefits of the Iris F1 compared to traditional spectrometers are high speed, high resolution, parallel multi-wavelength, and high brightness. What it means in terms of applications is that basically the high speed allows you to measure fast processes or high throughput applications. The high resolutions allows you to measure small molecules or avoid interferences. For example, if you measure broadband absorbers and you want to understand water interference. Then the parallel multi-wavelength nature allows you to measure complex mixtures and processes, and the high brightness is really a lifesaver when you go to real-life samples which are optically thick or maybe a multipass configuration. We designed the Iris F1 with flexibility in mind. So here you see two possible configurations. On the left side, you see it can be easily used with an FTIR unit inside, an attenuated total reflection unit. Here, and on the right side, you see, for example, that we added also a drift cell. Other possibilities are shown here. So we have also done some successful stop flow measurements. That was done in transmission, or you can easily custom build your experiment that is shown to the right, because we basically use a standard optical bench, which allows you to be very flexible for your experiments. A big part of our activities at IRSweep is concerning laser sourcing. When we started out as a company, we had one frequency COM laser that we could offer to customers, and now I'm proud that we have basically more than 10 lasers we can offer stock. So from 1760 to 1,000 wave numbers, and we can also make other lasers on order from 2,200 to 900 wave numbers. One thing that I wanted to point out here is, you see we have like three wavelength or three lasers around 1650. So the 1675 wave number, the 1650, and the 1625, and they were developed specifically for bio applications. So we do develop lasers according to application needs, and it is important for us to hear from you as early as possible when you're interested in such an instrument, what kind of application you're targeting, because then we can basically start the sourcing of the laser. In terms of applications, as I said, we started with protein dynamics, but the fields of application has grown considerably since then. So we have now also combustion diagnostics, stopped flow, which you already saw some experimental setup, spectral electrochemistry, heterogeneous catalysis, VCD, polymer chemistry, and high-resolution spectroscopy, which is basically covered in this talk. I don't want to go too much into detail on those applications, because we try to have a complete set of webinars, scientific webinars, showing all those applications. And here you see 6 webinars on spectral electrochemistry, on combustion work, which is also available to view offline. So please go to the website irsweep.com/webinars, and you will have access to those webinars without any problems. So with this, I would like to actually give the screen over to Lucas so that we can hear this very exciting new development on the Iris F1 to allow high resolution and gapless dual COM spectroscopy.
Thank you, Andreas. I hope you can now see my screen which should look very similar to the one that Andreas showed. What I will present is essentially the fruit that we were able to pick from a project that is called ComTrace, which is a collaboration between EMPA, ETH Zurich, Professor Jerome Feist, in charge of the frequency quantum cascade lasers, IR sweep, and University of Neuchâtel, Professor Thomas Südmeier, who is mainly using locking techniques in the context of frequency QCLs. Before I start, it may actually be interesting to know, I'm sorry, what our background is, why we do trace gas analysis and high resolution frequency spectroscopy. Our background is really in trace gas analysis for atmospheric applications. One example is that we run the world calibration of the Global Atmosphere Watch for WMO, or we run the Swiss Air Quality Monitoring Network for Switzerland. And the nicest and most beautiful air quality monitoring station that we have is Jungfraujoch. On top of this mountain in the cupola here, we have a laboratory, and I'm showing this because in this lab we actually run a quantum cascade laser instrument that measures CO2 and CO2 isotopic species, mainly 13 CO2. And this is most likely the longest running quantum cascade laser in the world. It has been running for over 13 years now, continuously, essentially without interruption, up in this mountain lab. And what it does is it measures CO2. What you see here is the CO2 concentration with its seasonal cycle showing photosynthesis in the summer and more anthropogenic content in the winter, and a steady increase of about 2 ppm per year. On the lower panel, this is really unique in the world, we also measure the C13, which is very slightly decreasing and essentially giving us a signature of the fossil fuel CO2 that we emit into the atmosphere. Now, quite obviously, environmental applications are not the only ones that are important for high precision gas spectrometry, health, breath analysis, industry, transportation, especially when it's combustion engines, security, and fundamental sciences, with a very broad field of applications. They all want to look at gases, and we have to remember that gases are essentially very diluted systems. So compared to liquids and solids, we have very few molecules, and therefore we need very high sensitivity. And this is really the key in the mid-IR. We gain in sensitivity because we have the strongest absorption lines, we have the fundamental absorptions. In the case of CO2, we gain about 3 orders of magnitude in compared to the near infrared. For N2O, for example, it would be even 5 orders of magnitude. There are basically two approaches to measure spectra in the mid-IR. We have FTIR, which is a broadband technique with a glow bar, low resolution, and incoherent light. In contrast to this, we have laser spectroscopy, which is very typically narrow band, but very high resolution with coherent and bright light. And both have advantages and disadvantages. Now, the key here is that frequency comms really give us the best of both worlds. A frequency comm covers a significant part of the mid-infrared spectrum in the case of the QCL frequency comm, and it has very well-defined lines of emission here shown, which are separated by the comm spacing. And if you also know the carrier envelope frequency, then such a comm is very easily defined and well known. The challenge then becomes measuring such a comm, because a frequency comm will emit all the frequencies or all the colors at the same time. So at the detector side, we need to be specific in terms of frequency or color. This can be achieved by the dual comm setup. In a dual comm setup, we choose 2 frequency comms that have slightly different repetition rates. We can do then fast acquisition and high resolution by combining such 2 comms and giving us multi-heterodyning in the radio frequency space. If we now add a sample to one of these legs of our very simple setup, then the optical absorption, the optical signal we get, will also be transferred to the radio frequency and show up there. And therefore, with the dual COM setup, we get this frequency or color information for the whole COM range. If we go a little bit more into detail, our frequency COM source is a continuous wave free-running broadband QCL, which essentially relies on phase locking through 4-wave mixing. And the challenge is really to design such a QCL such that you have flat group velocity dispersion, which should also be close to 0. If we now take two such COM, do heterodyning and Fourier transform, that's what we get in the radio frequency domain. Although this setup is very simple and very powerful, it has some additional challenge. And this additional challenge lies in the fact that point spacing is not resolution. What do I mean by that? Each single line, here schematically shown, has a very high resolution, which is typically much better than 1 megahertz. However, we have a point spacing which is given by design by the size of the QCL, and that point spacing is much larger, typically about 10 gigahertz. If we now compare this value to the line width, the Doppler line width of a small light molecule, which is in the order of 100 megahertz, you can easily see that our point spacing is too large. We may actually miss the absorption feature of our target molecule. This is shown here at the bottom. So we have those schematically shown COM lines and the feature of our target molecule, which lies such that we don't really see it. Our approach now is relatively simple. We tune the frequency COMs. We tune one or even both of them by modulating the laser current. Through this approach, we get not only one situation, but we can change the position of the COM lines, and you see now schematically that we suddenly see the absorption feature. This is shown here in 4 steps, but in reality, we don't do 4 steps. We can do many thousand steps. So if you do 10,000 steps, essentially you cover the full point spacing with frequency compositions that take full profit of the very good resolution that we have for each COM line. However, this carries a cost. It carries the cost of doing many measurements, and that costs some time. So essentially, if we look at a representation of acquisition time and spectral point spacing, you can see that we can either measure very rapidly with a rather large point spacing, or we can still measure rapidly but not as fast and get outstanding point spacing here, many points covering our spectrum. And we compare this to a number of mid-IR frequency COMs shown here in the middle, and you can see that with the quantum cascade lasers, we can actually go to the extremes. So already in 2018, Jessica Klock has showed that she can do very fast measurements. And what Michele will show now is essentially that we can also do very high point spacing, so get the full spectral information. And essentially, what we should realize is that by choosing the parameters right, you can cover the whole range between these two options, between these two extremes. And with this, I would like to give the screen to Michele, who will show the corresponding experimental results.
Yes, thank you, Lucas. I'm going to change to my screen now. Here we are. So the measurements I'm going to show you were taken with an Iris F1 spectrometer, where we've done some modification here for this study. We have 2 frequency combs with a center wavelength The configuration, the optical layout is phase sensitive dual comb. So we only have the interrogating comb passing through the sample. And also we have a second detector here for normalization. And we now modulate the current of both the interrogating and the local oscillator combs. And what this does is it shifts the emission spectrum of both combs. And in the next measurement, I'm going to show, this was the sweep was done over 120 milliseconds. This is where the acquisition takes place. And then we have about 800 milliseconds here where we allow the lasers to return to the initial state, and we use this time to save the raw data. At this wavelength, 1200 wave numbers, methane has a lot of absorption lines, so it makes a very good test candidate. So here we have a measurement where we sweep the current of the laser in 120 milliseconds, during which we have obtained eventually about 30,000 interferograms, and this leads to a point spacing that is about 300 kilohertz. The laser itself has a free spectral range of 10 gigahertz, so this is the natural spacing. If you divide this by 30,000, you get about this. And the resolution is approximately the same. On the right, in the top panel, you can see the measurement in red. The light trace is a single sweep, and the darker one is 22 sweeps co-averaged. This is methane, 107 millibars. And in blue is a simulation based on high trend data. There are two insets that show the spectra or the spectrum of methane at two different places, where you can see that we really have a continuous, a gapless spectrum. Because it's a phase sensitive configuration, we also have the dispersion, which is shown here at the bottom. On the left here, we have a close view on one of the absorption lines. Here on the left, this is the natural point spacing and resolution after interleaving, so about 300 kilohertz. We have a residual absorbance noise of 5.5 times 10 to the minus 2. And of course, we can, if we don't need this very large point spacing, such as in this case, we can always reduce the resolution and have less independent points, but we still have the full line shape. So this is 120 milliseconds. We can also do this significantly faster. We just have to increase the slope of the tuning ramp. Here, this is done in 6 milliseconds. Now, obviously, we have a much less, so it's 20 times faster. So we have 20 times less interferograms. That means 20 times less intermediate steps, and this results in a point spacing that is now somewhat larger. But of course, we gain the temporal resolution here. And again, on the right it's the same sample as before, measured with this spectrometer. And again, on bottom left, we have a close view on that same transition as before. We now have, of course, fewer points because the measurement is much faster, and the noise level is of the order of 3 times 10 to the minus 2 absorbance. Now I would like to say a couple of words about the frequency axis. Here you see we have an absolute frequency axis, but these lasers are free running, so we somehow need to calibrate this to determine this axis. And the way we've done this here is the following. We know that the frequency of a comb line, of the interrogating comb, is time dependent because we change or current dependent, if you like, since we change the current with time, and it depends on an integer. Let's call it x, which is just the index of the comb line. And because it is a frequency comb, we have a relationship. If we know the frequency of one specific comb line, say x0 at a given time, and if we know the comb spacing, which is this is the free spectral range of the laser at that instant, then we can compute all the other frequencies as well. And this is given by the fact that it's a frequency, that the source is a frequency comb. And now we make an assumption here about these two frequencies. So the optical frequency of one comb line and the free spectral range, we assume that they change more or less linearly in time. We add a quadratic term because usually there is a bit of curvature in this. Now, when we measure the amplitudes of our beat notes, we can plot these next to one another. So this is shown here on the right in the various colors. So each color is the amplitude of one beat note, or if you want, the absorbance, so the reciprocal of the amplitude of a beat note as a function of time. So we have a time axis that goes from, say, here from 0, where my pointer is, to 6 milliseconds, that's the sweep, and then it starts over 0 to 6 milliseconds and so on. So I've simply put all these traces next to one another and not on top of one another, but of course they are measured simultaneously. And it is now relatively simple to identify, if you have a known spectrum of methane, to identify what these absorption lines that are labeled as A, B, C, and D are. So we know on which beat note they occur. So we know they're the beat note index. And we know at what time during the sweep they occur. We can just read this out from this plot, and we can look in HYTRAN what the correct center frequency is. Okay, and if we do this, then we can solve the following problem. We have the known frequencies of these transitions, and we have the frequencies of these transitions as predicted by this model that we have here at the top, which now contains these 6 free parameters. And we essentially just minimize this, and we do a least square fit. And that then gives us a frequency axis we can compute for each beat note and at each time of the sweep at what frequency it was. And this we can then verify how good this is. So here we have the center frequency of the absorption lines. In red are the ones that were used for calibration. We haven't used all of them. There's hundreds of them. And in blue are some additional ones just for validation. This is the true center frequency, and on the vertical axis is the error. So this is the difference between what HYTRAN says where the frequency, where the center should be, and what we get after having done the fit. And you can see that we are usually within plus minus 0.002 wave numbers. Finally, a word about noise, or the signal to noise of the measurement. This is a typical beat note spectrum. You see we have some beat notes that have a very large amplitude, very good signal to noise, 40, 50 dB over the detector noise, and some are weaker. So of course the signal to noise in the spectrum, as you've seen before, will depend on the position here on the chosen beat note. And what we've done here, we have selected a strong, a medium, and a weak beat note, and we have measured their amplitude for several hours. And we have determined what the absorbance noise would be. That's the top row in this here on the right. And we have also determined what the phase is. You can really see there's some drift in the phase. This is an interferometric measurement, so every change in the length of the arms of the interferometer will be detected. And we can then from these do compute Allan plots. Essentially, we can compute the absorbance, root mean square noise, or the phase noise as a function of co-averaged sweeps. And I think the key message here is that for the very strong beat notes, we have some excess noise that we don't really know where it's coming from, but the vast majority of the beat notes are detector noise limited. So we can gain some signal to noise by co-averaging multiple sweeps. So with this, I am at the summary. So I have what we have shown here is that we can do current tuning on the local oscillator and the interrogating comb, and we can then interleave the data that we obtain this way, and therefore thereby reduce the spectral point spacing from the natural spacing, which is usually of the order of 10 gigahertz to below a megahertz. We can measure the complete line shape, even of Doppler Broden transitions. And in particular, we have shown Gapless spectra here spanning 50 wave numbers with sub-megahertz resolution in 120 milliseconds, or with a slightly larger resolution of 10 megahertz in about 6 milliseconds. This concludes my presentation.
Thank you to Lucas and Michele for this great and interesting talk. With this, we open the question and answer session. I've actually already quite numerous questions in the Q&A section. So let me just go through them as they came in. So the very first question was, you can measure down to less than 0.001 wave number accuracy within 120 milliseconds, which is outstanding. What is the theoretical limit of the IRIS F1 spectrometer and spectral resolution when you would apply this technology over a longer time frame of 1 to 2 minutes? So I guess the question is, what is the stability over longer time scales? Maybe Michele, can you comment on that?
Yes, so the lasers are free running, so they will experience some drift over time. So this line width of 1 to 300 kilohertz is obviously not going to apply over several minutes. So this would lead to a reduction in the resolution. Well, not a reduction, a deterioration in the resolution. We haven't measured this. I mean, it's actually quite difficult to measure, because even with Doppler Broden transitions, you still have line widths of 100 megahertz, and we expect drifts to be of the order of a couple of megahertz. So if we measure over several minutes, we expect that the optical frequencies will be stable or reproducible within a couple of megahertz.
That's actually true. So it's like 1 or 2 megahertz. You can measure it in the heterodyne signal, the drift.
Yeah.
It is of course the drift of the two lasers, but it is stable within a few megahertz over minutes. That is correct. Then there is a question about the baseline. So basically, in the methane spectrum, is there an underlying echelon on the baseline? What is this from?
Yes, it's from the windows of the single pass cell. In that measurement, the background measurement was not the empty cell, but was actually the cell removed from the path. So the sample is the gas plus the windows. That's why we have an echelon, and also why there is an offset. The absorbance is slightly above 0 everywhere. This is because of the absorption from the window.
I actually have a follow-up question there. Is it hard to remove such echelons when you measure them, or is the broadband nature helping, the broadband high resolution nature?
No, I mean, you should take the background measurement with the cell in the path, and then you have the echelon on the background trace, and then hopefully you can divide it out. It just wasn't done in this measurement because it was easier to remove the cell as a whole.
Okay. Yeah, so basically the comment is wedged windows would help. Is that also?
Yeah. We have a different cell now, and the AR coating as well, of course, would help.
Okay, good. Then there are two questions relating to water vapor. Have you had problems with water vapor in these measurements, and how do you correct for water vapor? I guess they're sort of related, so maybe we can address them at the same time.
Well, we don't, in these measurements, we don't have problems with water vapor. I think that if you go towards 1350 wave numbers, then yes, then you will have problems. But here we don't actually see any water vapor.
And I guess then you could use the high resolution broadband nature to actually also fit the water so it's basically as a gas you measure.
Yes, I mean, if it's in the sample, yes. If you mean in the instrument, you can just purge the instrument like you do with an FTIR, of course.
Yeah, that is of course also true. So there's another question, which is with your calibration technique that you applied, do you think that the Iris F1 is well adapted to line frequency measurement?
Honestly, I don't think so, because 0.001 wave number is more or less what we have from as precision or as accuracy from the calibration. And if you're happy with that, well then yes, but I think that normally for lines, if you really want to measure line centers, you need something better than that.
Exactly. So basically, you need to track. You need a better reference for this, which is possible. Yeah, it can be addressed, and I think it's important to say that this was not the goal here in this work. So yeah, there's another comment on the wedged windows, which we addressed, that it would help. Mm-hmm. I have a personal questions actually. So you have shown the latest results, the 6 millisecond. What do you think is the limit? I mean, 6 milliseconds. It really starts to become very attractive also for combustion work. What do you think? How far can it be pushed?
Well, you can of course decrease it to any level you like, but then you are decreasing the number of intermediate steps in your interleaving, and then therefore you're increasing the spectral point spacing. So you can always trade one for the other. I think what you have to keep in mind is that there is a minimum duration for an interferogram, which is given by the spacing of the beat nodes. So for these kind of measurements, that duration is roughly just order of magnitude 1 microsecond. So if you now want to take, if you want to reduce the natural point spacing, which is, let's say, 10 gigahertz to 10 megahertz, you need 1,000 intermediate steps, and 1,000 times a microsecond gives you a millisecond. Mm-hmm. So 10 megahertz point spacing, a millisecond is and what we have is 6 milliseconds and 7 megahertz. So there's probably a factor 2 or 3 that can be gained there. If you're happy with 100 megahertz point spacing, then of course you can go below a millisecond easily.
Mm-hmm. Yeah, it's actually it's what Lucas showed, had this graph where this axis over which we can basically optimize the system to adapt for specific applications. Yeah, that's I agree with this. So I have covered all the questions which are written. If you have any more, feel free to write it down. We're here still to answer your questions. Please post them in the Q&A session. And otherwise, of course, you're always welcome to contact us, HireSweep or EMPA, if you have questions on the specific work. With this, I would like to conclude the webinar. And I would like to make a bit of advertisement for the following webinars. We will actually hold this instrument, the high resolution option. We are developing a special version together with Muriel Lepere, and we will showcase this new kind of high resolution instrument that you can now acquire from HireSweep together with her in the next webinar on the 9th of July this year. So please, if you're interested in high resolution measurements, make sure to follow that. This one will be not optimized for high speed, but rather for high accuracy measurements. And then also a webinar on the 16th of July with Joachim Heberle, more on bioapplications on rapid reaction monitoring of proteins with dual-com spectroscopy. So with this, I would like to thank all our participants of this webinar, and I hope to hear from all of you soon. Have a good day and see you soon. And thanks again to Lukas Emenecker and Michele for this very, very interesting and great talk. Thank you.